Have you ever learned a bunch of controller algorithms only to realize you don't know the actual system model? Have you ever derived a model but found yourself stuck not knowing the parameters? This video will use a DC motor as an example to teach you how to deal with these issues. This is your control theory teaching assistant. Before designing a controller, it is usually necessary to understand the characteristics of the system. There are two ways to do this. The first way is to derive the model using physical formulas. This method allows for obtaining a complete system model, and allows for appropriate simplifications. For example, a motor model is divided into a mechanical model and an electrical model. The electrical model includes the torque generated by the electromagnet, and the back electromotive force, EMF, produced during rotation. The mechanical model includes the load driven by the torque, and the frictional forces. Combining the two gives us the model of the DC motor. Since the inductance is smaller than the resistance, and the electrical system's response is much faster than the mechanical system's response, further simplifications can be made. However, the drawback is that obtaining a complete model of the system is quite challenging. Therefore, I personally recommend beginners use the second method. The second method is to guess the system's model. For example, if the system's response looks like this, we can guess it is a first-order model. If the system's response looks like this, we can guess it is a second-order model. Take a DC motor as an example. If the input is voltage and the output is speed, it will look like this. At this point, it is quite reasonable to assume that the velocity-voltage relationship is a first-order model, and the position-velocity relationship is an integrator. Moreover, if the physical model of the DC motor is appropriately simplified, the same results can be obtained. After obtaining the system's model, the next question is how to obtain the model parameters. There are 4 ways. First, use the parameters provided by the motor, such as the torque constant and the back EMF constant. Second, use measurements, such as the motor's resistance, inductance, and moment of inertia, which can also be calculated. However, the problem arises with the viscous friction coefficient, which cannot be directly measured. Therefore, I personally recommend the following 2 methods. Third, identify characteristic points of the response and back-calculate the model. For example, when a DC motor is supplied with voltage and the speed response looks like this, we can use the time to reach 63% of the final value as the time constant. The steady-state speed can also be used to back-calculate the DC gain of a first-order model. Dividing both the numerator and the denominator by the time constant, we can obtain the familiar form of a first-order model. Finally, my favorite approach: use a fitting method. Simply input a voltage to make the motor rotate forward and backward, record the applied voltage and the measured speed, and then use MATLAB's TFS function to calculate the parameters. This method has numerous advantages, such as simplicity, high efficiency, and the ability to quantify how well the fitted model matches the actual response, determining if it is accurate or not. In conclusion, before designing a controller, it is necessary to perform modeling to obtain the system's model. The parameters can then be determined through system identification. For example, with a DC motor driven by voltage, it is reasonable to assume that the velocity-voltage relationship is a first-order model. By recording the applied voltage and the motor speed, the parameters of the model can be calculated using MATLAB's TFS. The next video will explain how to implement system identification. See you next time.